Sacramento, California. February 6, 1883. In the pre-dawn darkness, a glow emanates from the windows of the Central Pacific Railroad's massive locomotive works along the Sacramento River waterfront. Inside, master mechanic Andrew Jackson Stevens stands before something that has never existed before. The frame alone stretches across the shop floor in two massive cast-iron sections, each requiring its own casting pour because no foundry crucible in California can hold enough molten metal to form the whole. 5 pairs of driving wheels, each standing nearly 5 feet tall, wait to be mounted. When complete, this machine will weigh 77 tons and measure over 60 feet from pilot to tender. It will be the largest locomotive in the world. Stevens runs his hand along the cold metal, calculating pressures and volumes in his head. The cylinders he has designed measure 21 inches in diameter with a 36-inch stroke, dimensions that promise tractive effort approaching 33,000 pounds. But there is a problem Stevens knows and cannot yet solve. The boiler, constrained by the width of standard gauge track and the clearances of tunnels and bridges, may not be large enough to feed those massive cylinders. The fire grate measures just 42 square feet. The heating surface totals only 1,900 square feet. These numbers gnaw at him, but Railroad President Leland Stanford has ordered construction to proceed without delay. The Southern Pacific Network needs power to haul freight trains up the brutal grades of Tehachapi Pass, and Stanford believes size alone will deliver it. Outside, the first light touches the Sierra Nevada peaks to the east, the same mountains Central Pacific carved through 15 years earlier to complete the Transcontinental Railroad. That achievement required different machines, lighter and nimbler, designed for speed across plains and stability through rock tunnels blasted by Chinese workers wielding black powder and hand drills. But now, in 1883, the railroad faces a different challenge. Traffic has exploded. Freight tonnages that once seemed impossible now arrive daily. The old 4 Neil Americans, those elegant wood burners that symbolized the conquest of the continent, cannot keep pace. What Stevens is building in this shop, a 410 monster they will name El Gobernador after the state's governor, represents an attempt to solve through sheer mass what earlier generations solved through multiplication. Instead of running 2 locomotives, run one twice as large. This gamble, this leap toward gigantism, will define the final years of the Wild West Railroad era. It will also fail. The story of the largest trains in the American West is not a simple tale of progress. It is a story about the violent collision between ambition and physics, about men who believed they could conquer mountains with enough boiler pressure, and about the stubborn reality that the biggest machine is not always the best. Between 1869, when the Golden Spike joined the Union Pacific and Central Pacific Rails at Promontory Summit, Utah, and 1890, when the Census Bureau declared the frontier closed, American railroads underwent a transformation as profound as any in industrial history. The locomotives that inaugurated transcontinental service weighed around 32 tons and could haul perhaps 15 freight cars on level ground. By the end of the 1880s, machines like El Gobernador promised to more than double that capacity. This expansion was not smooth, not inevitable, and not always successful. It was purchased with millions of dollars in capital, thousands of engineering experiments, and an unspoken bargain. The West's resources, extracted and shipped east, would fuel the growth that made these giants necessary in the first place. The question at the heart of this history is not merely which trains were largest, but rather what did largest mean and what costs did size extract? To answer these questions requires examining not just the dimensions of locomotives, but the entire system that surrounded them. The grades they climbed, the coal they burned, the fortunes they built, and the limitations they could never quite transcend. In May 1869, when Central Pacific's Jupiter and Union Pacific's No. 119 touched cowcatchers at Promontory Summit, They were nearly identical machines despite being built on opposite coasts. Jupiter, constructed in September 1868 by the Schenectady Locomotive Works in New York, weighed 65,400 pounds and stretched 41 feet 2 inches from pilot to tender. Its 4 driving wheels measured 60 inches in diameter. 2 cylinders, each 16 inches across with a 24-inch stroke, generated 10,190 pounds of tractive effort. It burned wood, consuming vast quantities of Sierra Nevada timber to maintain steam pressure of 140 pounds per square inch. Union Pacific No. 119, built by Rogers Locomotive and Machine Works in Paterson, New Jersey, in November 1868, weighed slightly more at 68,400 pounds and measured 41 feet 10 inches in length. It burned coal hauled from the Wyoming mines that Union Pacific would soon dominate. Both locomotives represented the 4-4-0 wheel arrangement, known as the American type, which had dominated U.S. railroads since the 1840s. These machines were not small by the standards of their day. They represented significant capital investment. Jupiter cost approximately $25,000, equivalent to perhaps $700,000 in modern purchasing power. But they were not giants. A typical 4-4 Neo could haul 15 to 20 loaded freight cars on level track, perhaps 10 cars on a 2% grade. This meant that a fully loaded freight train in 1869 might stretch 300 feet from locomotive to caboose and carry perhaps 100 tons of payload. Passenger trains were heavier relative to their length due to the substantial weight of wooden passenger cars, but they rarely exceeded 8 or 9 cars even on major routes. By comparison, a freight train on the same route 20 years later might run 40 cars and carry 400 tons. The transformation began in earnest after the financial panic of 1873. The depression that followed bankrupted numerous railroads but also created the conditions for consolidation. Larger railroad companies absorbed smaller lines, standardized their operations, and began to think systematically about locomotive design. The Pennsylvania Railroad, already the largest railroad in the world by the mid-1870s, made a crucial decision in 1875. It designated the 2-8-0 consolidation type as its standard freight locomotive. This choice signaled a fundamental shift in thinking. The consolidation, first built by Baldwin Locomotive Works in 1866 for the Lehigh and Mahoney Railroad, featured 8 driving wheels arranged in 4 pairs, giving it substantially more adhesion than the 4-4-0 American. A typical 2-8-0 of the mid-1870s weighed between 75 and 90,000 pounds, with perhaps 55,000 pounds on the drivers. This translated to roughly 50% more tractive effort than a 4-4-0 of similar vintage. The impact on freight operations was immediate. Where 2 4-4-0s had been required to haul a train over mountainous terrain, a single 2-8-0 could often do the job. The economics were compelling. Running 1 locomotive instead of 2 meant 1 engineer, 1 fireman, 1 set of maintenance costs, half the coal consumption. The Erie Railroad began replacing its 4-4-0s in freight service with 2-8-0s in 1875. Other roads followed. By 1880, the United States had 17,800 freight locomotives and 22,200 passenger locomotives in service, together carrying 23,600 tons of freight. The shift toward larger, more powerful machines was accelerating, but size brought complications. Larger locomotives required stronger track, heavier rails, better roadbed. The iron rails of the 1860s, weighing perhaps 56 pounds per yard, could not support the pounding delivered by 80,000-pound locomotives with their hammering pistons and surging momentum. Railroads began laying steel rails, first imported from England and later produced in American mills, with weights climbing to 70 pounds per yard by the late 1880s. Bridges required reinforcement or replacement. The spectacular wooden trestles that had carried construction trains across western canyons could not bear the weight of the new machines. Stone arches and iron truss bridges replaced them at enormous cost. Turntables had to be lengthened. Roundhouses had to be expanded. Water towers had to pump faster to fill larger tenders in the brief minutes locomotives stopped at division points. The costs were staggering. Laying a mile of new railroad track with steel rails, proper ballasting, and heavy timbers could cost $10,000 or more by the 1880s. Replacing a wooden trestle with an iron bridge might require $100,000. These investments made sense only if traffic justified them, and in the booming West of the 1870s and 1880s, traffic grew explosively. The Comstock Lode silver mines around Virginia City, Nevada, generated freight tonnages that seemed impossible just years earlier. The Virginia and Truckee Railroad, chartered in 1868 to haul ore from Virginia City to the mills along the Carson River, became one of the most profitable short lines in America, despite stretching only 52 miles at its peak. The engineering required to build this line was extraordinary. Surveyor Isaac James held the grade to a maximum of 2.2% as the railroad descended 600 feet in 13.5 miles, requiring the track to make the equivalent of 17 complete circles through cuts, fills, and curves. The Virginia and Truckee's success illustrated both the potential and the limits of the largest trains in the Wild West. During the peak years of the Big Bonanza silver boom between 1876 and 1877, the railroad operated 22 locomotives and 361 freight cars. At the height of the boom, the line scheduled 30 to 45 trains per day on single track, an operational tempo that required precise timing and absolute discipline. The freight volume reached 400,000 tons per month. To put this in perspective, this meant the railroad was moving approximately 13,000 tons per day, or roughly 650 carloads, on a line that required constant climbing and descending through steep mountain terrain. Each locomotive might make 2 or 3 round trips per day, hauling perhaps 8 to 12 loaded cars up from the mills or down from the mines. The ore itself was dense and valuable, making efficient transportation critical to profitability. The Virginia and Truckee initially used 2 to 6 narrow mogul-type locomotives purchased from H.J. Booth and Baldwin Locomotive Works. These machines weighed between 40 and 50,000 pounds and were designed for slow, heavy work on steep grades. By the mid-1870s, the railroad had standardized on the 4-4 or American type for passenger service and the 2-6 for freight, occasionally renting larger 4-6 10-wheeler types from the Central Pacific for particularly heavy trains. The railroad's shops in Carson City, proclaimed by Central Pacific as equal to their own massive facility in Sacramento, could build or rebuild almost any locomotive component. This self-sufficiency allowed the Virginia and Truckee to maintain its demanding schedule even when equipment broke down or required major repairs. The financial returns were extraordinary. In the late 1870s, stockholders received monthly dividends exceeding $100,000. The railroad paid for itself within a few years of operation. But this success came with an expiration date. Silver production from the Comstock peaked in 1877 and then collapsed as the ore bodies played out and flooding problems became insurmountable. By 1880, traffic had fallen precipitously. The Virginia and Truckee kept operating, shifting to timber and agricultural products, but it never again matched the frenetic intensity of the Big Bonanza years. The railroad's experience demonstrated a crucial reality. The largest trains and the most intensive operations appeared not where railroads wanted them, but where geology and economics created temporary abundance. When the mines flooded, no amount of locomotive power could sustain the traffic that had justified such intensive investment. Meanwhile, the transcontinental railroads confronted different challenges. The Central Pacific, having conquered the Sierra Nevada, spent the 1870s expanding its network across Nevada and into Utah. The railroad also began manufacturing its own locomotives at its Sacramento shops. In 1872, master mechanic A.J. Stevens rebuilt Central Pacific No. 73, a 4-4 that had been damaged in a collision. transforming it into what became the template for future Central Pacific construction. Over the next decade, the Sacramento shops would build dozens of locomotives based on Stevens' designs, making the Central Pacific one of the few American railroads to manufacture its own motive power on a significant scale. This capability would prove crucial when Stevens began designing the giant locomotives of the 1880s. In 1882, Stevens built Central Pacific No. 229, an experimental 480 locomotive unofficially named Mastodon. This machine represented a significant departure from earlier designs. With 8 driving wheels arranged in 4 pairs and a 4-wheel leading truck for stability, the Mastodon weighed approximately 100,000 pounds and developed tractive effort approaching 30,000 pounds. The locomotive was designed specifically for freight service over the steep grades east of Reno, where the Central Pacific Line climbed through the Humboldt Range and across the deserts of Nevada. The Mastodon succeeded in its assigned task, hauling trains that would have required double heading with smaller locomotives. Encouraged by this success, Stevens and Central Pacific President Leland Stanford began planning something even larger. What emerged from the Sacramento shops in February 1883 was El Gobernador, the 410 locomotive that would briefly hold the title of largest locomotive in the world. The specifications were astounding. 10 driving wheels, each 57 inches in diameter, promised adhesion that would allow the locomotive to start trains weighing hundreds of tons on steep grades. The cylinders, measuring 21 inches in diameter with a 36-inch stroke, were among the largest ever fitted to a locomotive at that time. The engine's weight of 146,000 pounds, later increased to 154,400 pounds after a rebuild, dwarfed any previous design. Stevens equipped El Gobernador with his own valve gear system, using 2 valves per cylinder to improve steam distribution and reduce clearance volumes. But the design contained a fatal flaw that Stevens either did not recognize or could not overcome given Stanford's impatience. The boiler was simply too small for the cylinders. With a fire grate area of only 42 square feet and total heating surface of approximately 1,900 square feet, the boiler could not generate steam fast enough to keep pace with the demands of those enormous cylinders. During test runs around Sacramento in 1883, while the locomotive was supposedly being prepared for service, railroad officials kept El Gobernador under steam near the passenger depot. When eastbound trains arrived, the locomotive would steam past, hauling a long string of empty freight cars, impressing passengers and generating publicity. But the engine did not enter revenue service until March 1884, more than a year after its completion. Even then, its performance was disappointing. Firemen struggled to maintain steam pressure. One frustrated crewman reportedly declared, "All hell couldn't keep steam up in that engine." The problem was fundamental. The cylinders consumed steam faster than the boiler could produce it. During hard pulling, boiler pressure would drop, reducing power output and slowing the train. Central Pacific attempted several fixes. In 1885, the railroad rebuilt El Gobernador with smaller cylinders, reducing their diameter and attempting to better match them to the boiler's capacity. The modification helped marginally, but did not solve the underlying problem. The locomotive remained a disappointment, unable to deliver the performance its size suggested. By the late 1880s, Central Pacific had largely abandoned using El Gobernador for regular service. The machine was scrapped on July 15, 1894, having served barely a decade, though its boiler remained in use as a stationary steam generator for the Sacramento shops until 1905. El Gobernador's failure illustrated the central problem facing locomotive designers in the Wild West era. The constraints of standard gauge track made it extraordinarily difficult to build machines that were both large and properly proportioned. A locomotive's boiler had to fit between the rails and beneath the loading gauge that defined maximum height and width. This limited the volume of water the boiler could hold and the area of heating surface available to convert that water into steam. Cylinders, by contrast, could be made as large as desired, at least in theory. But there was no point building massive cylinders if the boiler could not feed them steam. The most successful large locomotives of the 1880s, like the Pennsylvania Railroad's growing fleet of 280 consolidations, achieved their power not through dramatic size increases, but through careful balancing of all components. A well-designed 75,000-pound locomotive would outperform a poorly designed 100,000-pound machine every time. This lesson came slowly to the railroad industry. Throughout the 1880s, various railroads experimented with increasingly large locomotives, seeking the elusive combination of power and efficiency. The Lehigh Valley Railroad built its champion in 1880, a 480 designed by Philip Hofker that briefly held the record for largest locomotive before El Gobernador surpassed it. The Great Northern Railway would later build its G5 class 480s in 1897. Continuing the search for size. But none of these machines achieved lasting success. They were too heavy for the tracks of their era, too complex for the maintenance facilities available, and too often poorly proportioned. The real workhorses of Wild West railroading remained the more modest 440s, 460, and 280 types. These locomotives, weighing between 50 and 90,000 pounds, could be maintained at division point shops with standard tools and parts. They could navigate the tight curves and steep grades of mountain railroading. They could be doubled in use of helper service when traffic demanded. Most importantly, they worked reliably, day after day, year after year. Union Pacific, Central Pacific, Southern Pacific, Atchison, Topeka, and Santa Fe, all the major Western railroads relied primarily on these types throughout the 1870s and 1880s. The giant locomotives grabbed headlines, but the mid-sized machines moved the freight. Consider the operational realities. A typical freight train in the mid-1880s on a major Western route might consist of 25 to 35 cars hauled by a single locomotive on level track, fewer on grades. Each boxcar could carry perhaps 15 tons of freight. A loaded freight train therefore moved perhaps 400 to 500 tons of payload. The locomotive, tender, and caboose added another 100 tons. Total train weight approached 600 tons. On a ruling grade of 2%, common in mountain railroading, a locomotive needed roughly 100 pounds of tractive effort per ton of train weight to maintain even minimal speed. This meant the locomotive needed to develop 60,000 pounds of tractive effort to pull this train up the grade at perhaps 10 or 12 miles per hour. A typical 280 of the 1880s developed between 25 and 35,000 pounds of tractive effort, meaning helper locomotives were essential for mountain work. The economics of helper operations were complex. A helper locomotive required a crew, consumed fuel, and had to be returned to its starting point after assisting a train over the summit. Railroads tried to minimize helper districts, but geography imposed limits. The Central Pacific could not eliminate the need for helpers over Donner Pass. The Southern Pacific could not avoid helper service at Tehachapi. Union Pacific required assistance over Sherman Hill. These operational realities meant that building individual locomotives, much larger than about 100,000 pounds, produced diminishing returns. A machine that was too large could not operate over much of the railroad's network. It required special handling, specialized maintenance, and inflexible routing. The theoretical gains in tractive effort were often negated by operational complications. Passenger service presented different constraints. Passenger trains were lighter than freight trains but needed to maintain higher speeds to meet published schedules. The 440 American type remained the dominant passenger locomotive throughout the Wild West era because it combined adequate power with excellent speed potential. Those large 60-inch driving wheels could turn fast, allowing sustained speeds of 45 or 50 miles per hour on level track. Passenger comfort required smooth riding, which meant locomotives needed good suspension and careful balancing. The largest locomotives, with their massive frames and numerous driving wheels, often rode roughly, subjecting passengers to jarring motion. Railroad managers learned that passenger service rewarded refinement more than raw size. The dining car, introduced in 1867, and the sleeping car, which became common in the 1870s, added substantial weight to passenger trains. A fully loaded sleeping car might weigh 60 tons. A dining car, with its kitchen equipment, provisions, and staff, could reach 50 tons. A complete passenger train of 8 or 9 cars in the 1880s might weigh 350 tons, nearly as much as a freight train, but requiring perhaps twice the speed. This meant passenger locomotives needed both power and speed, a combination that was difficult to achieve. The most successful passenger locomotives of the era, like the 4-6-neo 10-wheeler, which first appeared in 1847 but reached its peak of popularity in the 1880s, provided a practical compromise. With 3 pairs of driving wheels instead of 2, the 10-wheeler developed more adhesion and tractive effort than a 4-4-neo while maintaining good speed potential through careful design of driver diameter and cylinder dimensions. The numbers tell the story of expansion. In 1869, the Central Pacific had 162 locomotives in service. By 1880, the United States had nearly 40,000 locomotives in service. This explosive growth reflected the rapid expansion of railroad mileage, which increased from approximately 43,000 miles in 1869 to over 93,000 miles in 1880. The West accounted for a substantial portion of this expansion. New transcontinental routes appeared. The Atchison, Topeka, and Santa Fe completed its line to California in 1881. The Southern Pacific connected New Orleans to California in 1883. The Northern Pacific reached Puget Sound in 1883. Each new route required hundreds of locomotives and thousands of freight cars. The capital requirements were staggering, justifying the enormous financial power accumulated by railroad magnates like Jay Gould, Collis Huntington, and Leland Stanford. These men understood that controlling transportation meant controlling economic development. The largest trains represented more than engineering ambition. They embodied the belief that mastering logistics meant mastering the West itself. When Huntington pushed the Southern Pacific southward and eastward, he was not simply building a railroad, but constructing a mechanism to extract wealth from the territories the railroad penetrated. Freight rates gave the railroads enormous power over shippers. A farmer or miner who wanted to move products to market had no alternative to the railroad. The rates the railroad charged determined whether the farmer or miner could turn a profit. Railroad companies used this power aggressively, charging whatever the traffic would bear and adjusting rates to favor some shippers over others. The Interstate Commerce Act of 1887 represented Congress's attempt to regulate this power, but enforcement remained weak for decades. The largest trains, those massive freight operations moving hundreds of tons of ore, timber, and grain, generated the revenues that made railroad companies wealthy and powerful. The symbolic iron horse of the 1860s had become the industrial juggernaut of the 1880s, and its operators wielded economic power that rivaled or exceeded the political power of state governments. Labor relations reflected this power asymmetry. Railroad workers, from engineers to track laborers, worked under dangerous conditions for modest pay. The Great Railroad Strike of 1877, which began on the Baltimore and Ohio Railroad and spread across the country, demonstrated workers' willingness to fight for better conditions. The strike paralyzed railroad operations and required federal troops to suppress. It also revealed the stark reality of industrial railroad operation. Profit depended on minimizing labor costs, and workers had little recourse when railroads imposed wage cuts or demanded longer hours. Subsequent strikes in the 1880s, including the Great Southwest Railroad Strike of 1886, continued this pattern. By 1890, railroad labor relations had evolved into a permanent state of tension between capital and labor, with each side testing the limits of the other's power. The physical operation of the largest trains demanded extraordinary skill from railroad crews. An engineer controlling a 100,000-pound locomotive hauling 30 cars across mountain grades needed to anticipate every curve, every grade change, every water stop. Steam locomotives required constant attention to maintain proper boiler water levels and steam pressure. Too little water, and the crown sheet of the firebox could overheat and fail catastrophically. Too much water, and steam pressure would drop. The engineer monitored pressure gauges, watched the track ahead, and coordinated with the fireman who shoveled coal or threw wood into the firebox to maintain steam. A skilled fireman could anticipate the locomotive's needs, building fire before a grade and easing off at the summit to conserve fuel. Poor firing technique wasted fuel and reduced power output. Train handling required similar expertise. Freight cars in the 1880s used primitive Lincoln pin couplers that left slack between cars. Starting a train on a grade required the engineer to ease the locomotive forward, taking up slack gently to avoid breaking couplers or parting the train. Stopping required careful coordination between the locomotive's brake and the hand brakes mounted on each freight car. The conductor would signal the brakemen to set hand brakes, and they would climb atop the moving cars to turn the brake wheels, a procedure that killed dozens of brakemen each year when they slipped and fell. The Westinghouse air brake, invented in 1869 and improved throughout the 1870s, gradually replaced hand brakes, but did not become universal until the 1880s and 1890s. Even with air brakes, stopping a heavy freight train on a mountain grade required precise judgment to avoid either running away or stalling on the grade. Weather complicated everything. Winter snows could bury track, requiring armies of workers with shovels to clear the line. Railroads deployed various types of snow plows, from simple wedge plows pushed by locomotives to massive rotary plows that threw snow hundreds of feet to the side. The Central Pacific built miles of wooden snow sheds to protect track in the Sierra Nevada, essentially creating tunnels to prevent snow accumulation. Summer heat caused rails to expand and occasionally buckle, requiring track crews to watch for sun kinks. Floods washed out bridges and undermined roadbed. The Great Salt Lake Crossing, which Central Pacific began building in 1902 to bypass the circuitous route around the lake, would later demonstrate the challenges of railroad construction across unstable terrain, though this development came after the Wild West era proper. The question of what constituted the largest trains admits several answers depending on how size is measured. By gross weight, a heavy freight consist on a major route in the late 1880s might reach 800 or 900 tons, including locomotive, tender, and caboose, hauling perhaps 550 tons of payload in 35 to 40 cars. This would be among the heaviest trains regularly operated. By length, passenger trains could stretch 500 feet or more with 9 or 10 cars, though they rarely exceeded 400 tons in weight. By locomotive size, El Gobernador at 154,400 pounds held the record briefly, though its operational failure meant it never regularly hauled the heaviest trains. By traffic density, the Virginia and Truckee at its peak ran more trains per mile of track than perhaps any other railroad in the West, though its trains were relatively short. This diversity of answers reflects the complexity of Wild West railroading. The industry was young, rapidly evolving, and characterized by experimentation. Different routes faced different challenges. A railroad crossing the Sierra Nevada needed different equipment than one crossing the plains of Kansas. Lines serving mining districts operated differently than one hauling agricultural products. The search for the largest trains reflected the belief, common in that era, that size and power could overcome any obstacle. This belief proved partly true and partly false. Size helped, but only when properly applied. The modest, well-designed locomotives of the 1870s and 1880s proved more successful than the giants that grabbed headlines. The myth of Wild West railroading often emphasizes speed and drama. Locomotives racing across prairies, engineers leaning from cab windows, bandits stopping trains in remote canyons. The reality was more prosaic. Most railroad operation involved slow, careful work moving freight. The largest trains crept over mountain grades at 10 or 12 miles per hour, far slower than a horse could gallop. The drama lay not in speed, but in scale, in the systematic transformation of a continental economy through the patient accumulation of tonnage. Each trainload of ore moved one step closer to exhausting a mine. Each carload of timber brought deforestation 1 acre nearer. Each ton of grain represented a farmer's calculation that railroad transportation costs would leave enough profit to justify another season's planting. The environmental costs of these operations were rarely calculated at the time, but have become clearer with historical distance. The locomotives themselves consumed prodigious quantities of wood or coal. A wood-burning 4-4 might consume a cord of wood per hour of operation, meaning a day's work could require 8 to 10 cords. Central Pacific's operations in the Sierra Nevada consumed entire forests. Coal-burning locomotives in the 1880s might burn 3 to 4 tons of coal per 100 miles, translating to hundreds of thousands of tons annually for a major railroad. The smoke and cinders from these operations fouled the air in terminal cities and created fire hazards along the right-of-way. Sparks from wood-burning locomotives ignited countless forest fires. The social transformation was equally profound. Railroads brought markets to remote areas, allowing extractive industries to flourish. Mining camps that would have remained small without rail access grew into substantial towns. Agricultural regions that might have remained subsistence operations became commercial enterprises, shipping products hundreds or thousands of miles. The Wild West of popular imagination, with its cowboys and Indians and isolated frontier towns, was rapidly supplanted by an industrialized West integrated into national markets. The largest trains were both symbol and mechanism of this transformation. They represented industrial power, corporate organization, and the subordination of Western geography to Eastern capital. Indigenous peoples bore enormous costs from railroad expansion. The transcontinental railroads bisected hunting territories, facilitated military operations against native populations, and brought settlers whose presence made traditional lifeways impossible. The buffalo herds that had sustained plains tribes were systematically slaughtered, often shot from trains by passengers seeking entertainment. The Central Pacific's construction crews displaced northern Paiute and Shoshone people. The railroad corridors became corridors of disease as smallpox and other epidemics spread along the rail lines. The largest trains hauled not just freight, but the components of a new social order that had no place for indigenous sovereignty. The Chinese workers who built much of the Central Pacific, more than 14,000 men at the peak of construction, faced systematic discrimination both during and after their railroad work. They were paid less than white workers, given the most dangerous assignments, and then subjected to exclusionary laws designed to prevent them from settling permanently in the United States. The Chinese Exclusion Act of 1882 codified this discrimination at the federal level. Yet Chinese workers had made transcontinental railroading possible. They blasted tunnels through Sierra granite, laid track across Nevada deserts, and maintained the line after its completion. When the largest trains of the late 1880s hauled freight over Donner Pass, they traveled across infrastructure built largely by Chinese labor and paid for with Chinese lives. African American workers also contributed substantially to railroad operations. Sleeping car porters, beginning in the 1860s, were exclusively black men. The work was grueling and the pay modest, but it offered relative stability and became one of the few paths to middle-class status for black families in the late 19th century. The Brotherhood of Sleeping Car Porters, founded much later in 1925, would grow out of this workforce. Dining car staff, track maintenance crews, and locomotive maintenance workers included substantial numbers of black workers, especially in southern routes. Their contributions were essential to railroad operations but rarely acknowledged in contemporary accounts of the industry. Mexican workers, particularly in the Southwest after the Southern Pacific's completion to California, formed another crucial component of the railroad workforce. Track maintenance in the harsh desert environment required constant labor, and Mexican crews performed much of this work. The ethnic hierarchies of railroad employment reflected broader patterns of American racism, with white workers occupying the most skilled and highest-paid positions while workers of color were relegated to the most dangerous and lowest-paid jobs. Women's roles in Wild West railroading were limited by the social conventions of the era, but not absent. Harvey Houses, the chain of railroad restaurants established by Fred Harvey beginning in the late 1870s, employed young women as waitresses at remote western stations. These Harvey girls, as they became known, provided customer service and helped civilize the rough world of railroad travel. Some women worked as telegraphers, one of the few technical positions open to women in the late 19th century. The wives and daughters of railroad workers maintained households in railroad towns, providing the domestic labor that supported male railroad workers. Though invisible in most contemporary accounts, women's work sustained the railroad workforce. By 1890, when the Census Bureau declared the frontier closed, the railroad network that had seemed revolutionary in 1869 had become routine. The largest trains of the Wild West era had established patterns that would continue into the 20th century. Freight tonnages would continue to grow. Locomotives would become larger still, though the truly gigantic machines like the Union Pacific Big Boy of 1941 would not appear until diesel technology and improved track structure made them practical. But the fundamental transformation had occurred between 1869 and 1890. The Wild West had been conquered not primarily by cowboys or cavalry, but by railroad companies deploying systematic logistics and industrial organization. The largest trains represented the pinnacle of this industrial system. They were imperfect machines, often disappointing in operation, sometimes dangerous to their crews, and always expensive to maintain. But they worked well enough to move the freight that fed industrialization. The silver from the Comstock mines that Virginia and Truckee trains hauled to the mills found its way to mints in Carson City and San Francisco, where it became coins that circulated nationally. The timber from Sierra Nevada forests that Central Pacific trains carried to Nevada became mine timbers, railroad ties, and building materials for growing cities. The grain from California's Central Valley that Southern Pacific trains hauled eastward fed industrial workers in Chicago and New York. The coal from Wyoming mines that Union Pacific trains delivered to western cities powered factory boilers and heated homes. This was the true legacy of the largest trains of the Wild West. Not romantic adventure, but systematic exploitation of natural resources on an industrial scale. The machines themselves were remarkable achievements of mechanical engineering. El Gobernador, despite its failures, represented a bold attempt to solve real problems through innovative design. The Virginia and Truckee's operations during the Big Bonanza demonstrated what intensive railroading could achieve when traffic justified investment. The transcontinental railroads conquered distances that had required months of wagon travel and reduced them to days of rail journey. These were genuine accomplishments, but they came at costs that contemporaries largely ignored and that later generations have struggled to fully account for. The environmental degradation, the displacement of indigenous peoples, the exploitation of immigrant and minority workers, the concentration of economic power in corporate hands. These consequences flowed directly from the success of railroad operations. The largest trains were instruments of empire, not democratic institutions. They served the interests of railroad investors and Eastern manufacturers more than they served the interests of Western communities or workers. The wealth they generated accumulated disproportionately to a small class of industrialists, while the costs were borne by those with less power. The Wild West Railroad era also established patterns of corporate behavior that would shape American capitalism for the next century. The manipulation of stock prices, the rigging of freight rates, the corruption of political institutions through bribery and lobbying, the ruthless suppression of labor organizing, these practices all found fertile ground in the railroad industry of the 1870s and 1880s. The largest trains rolled across landscapes reshaped by corporate power, and that power showed little restraint. The Interstate Commerce Act represented one of the first federal attempts to regulate corporate behavior, but its enforcement was weak and its impact limited. Not until the progressive era of the early 20th century would serious regulation begin to constrain railroad corporate power. The technical achievements should not be minimized. Building locomotives that could haul hundreds of tons across mountain grades represented genuine engineering progress. The men who designed and built these machines solved difficult problems in thermodynamics, metallurgy, and mechanical engineering. A.J. Stevens' valve gear designs, though ultimately unsuccessful on El Gobernador, demonstrated creative thinking about steam distribution. The standardization of components that allowed railroads to maintain large locomotive fleets reflected sophisticated understanding of industrial organization. The development of air brakes, automatic couplers, and steel rails all represented important technological advances that made railroads safer and more efficient. But technology does not develop in a vacuum. The push for larger locomotives reflected economic pressures created by competition for freight traffic and the desire to reduce operating costs. The solutions engineers devised responded to these pressures. When El Gobernador failed to deliver on its promise, Central Pacific did not abandon the search for larger locomotives, but rather refined its approach, building smaller giants that worked better than the largest giant that did not. This pattern of incremental improvement, punctuated by occasional ambitious leaps, characterized technological development throughout the Wild West Railroad era. Consider the trajectory from the Jupiter of 1869 to the consolidation types of the 1880s. The 4-4 Jupiter weighed about 65,000 pounds and developed roughly 10,000 pounds of tractive effort. A typical 2-8 consolidation of 1885 weighed about 90,000 pounds and developed perhaps 35,000 pounds of tractive effort. This represented roughly 40% increase in weight, but 250% increase in tractive effort. The improvement came not simply from adding mass, but from better using that mass through improved design. More driving wheels meant more adhesion. Larger cylinders with longer strokes meant more power from each pound of steam. Better valve gear meant more efficient steam use. These incremental improvements delivered practical benefits that dramatic size increases often could not match. The limitations of Wild West Railroad technology became clear when compared to later developments. The locomotives of the 1880s burned enormous quantities of fuel to produce relatively modest power. A typical 2-8 might convert perhaps 6% of its fuel's energy into useful work at the drawbar. The rest was lost to exhaust heat, radiation, friction, and other inefficiencies. Later, superheated steam locomotives of the early 20th century would improve this to perhaps 10%, and diesel-electric locomotives would eventually reach 25% or more. The Wild West locomotives were thermodynamically primitive, but they represented the best technology available at the time. The mythology that grew up around these machines obscures their technical and operational reality. The image of the powerful locomotive conquering the wilderness appeared in countless paintings, photographs, and written accounts. Thomas Hill's painting, The Last Spike, showed the celebration at Promontory Summit, with the Jupiter and number 119 as central figures. Newspapers celebrated each new locomotive as the largest or most powerful ever built. The public imagination embraced the railroad as symbol of progress and American ingenuity. This mythology was not entirely false, but it was incomplete. It emphasized triumph and ignored cost. It celebrated conquest and overlooked destruction. It admired power and disregarded those who lacked power. The transition from Wild West railroading to 20th century railroad practice was gradual rather than abrupt. The locomotives of the 1880s continued in service well into the 1900s. Short lines and branch operations used 4 four-nose and 2 six-nose until diesel locomotives finally displaced them in the 1940s and 1950s. The operational patterns established in the Wild West era, with division points spaced by water and fuel requirements, with helper districts on mountain grades, with scheduled freight and passenger operations. These patterns persisted for decades. The social and economic relationships established in that era likewise showed remarkable persistence. Railroad companies remained powerful political and economic actors into the mid-20th century. Railroad workers continued to organize and strike for better conditions. The environmental consequences of railroad operations continued to accumulate. On a spring morning in 1890, a 2-8-no consolidation hauls a freight train over Donner Pass. The locomotive weighs 93,000 pounds, develops 38,000 pounds of tractive effort, and pulls 27 cars carrying 400 tons of freight. The engineer is a 40-year-old man who started as a fireman in 1872. He knows every grade, every curve, every water stop on this route. The fireman, 26 years old, shovels coal steadily to maintain steam pressure of 160 pounds per square inch. They will reach Reno in 4 hours, having descended 5,000 feet and traversed 70 miles of track. This is routine work, performed thousands of times each year, rarely noted in newspapers or celebrated in paintings. But this work, multiplied across thousands of locomotives and millions of miles, represents the true story of the largest trains of the Wild West. Not individual giants, but systematic operation. Not dramatic triumph, but steady accumulation. Not romantic adventure, but industrial labor. The machines that hauled these trains were the largest that American railroads could practically build and operate given the constraints of 19th century technology and infrastructure. They pushed against the limits of what was possible with cast iron frames, wrought iron boilers, and steam power. Some, like El Gobernador, pushed too far and failed. Most, like the countless 440s, 2 six-nose, 4 six-nose, and 2 8-sows that moved the freight and passengers, succeeded by being large enough but not too large. They represented a practical solution to practical problems, not heroic conquest, but competent engineering, not untamed wilderness, but industrialized landscape. This was the achievement and the legacy of the largest trains of the Wild West, and it matters more than the myths that grew up around them.